Welcome to today's class. We are almost done with our physics. Today, we are going to be looking at everything that has to do with wave and particles. Wave and particles. Welcome. Understanding wave can be defined as a disturbance. Wave can be defined as a disturbance. It is said to be what? A disturbance. All right. This particular disturbance travels through something called a medium. It travels through a medium. Through a medium. And this medium, sometimes it can be called material medium. What do we understand by this word medium? It's just a means of travel, a vehicle that transports wave. Wave is a disturbance. Yes, the medium is a vehicle that transports wave. All right. So, it travels through a medium, transferring energy. You can also say spreading energy. Transferring energy from one place to another without transferring matter. Without the transfer of what? Matter. In essence, it doesn't cause a permanent disturbance to this medium itself. So, wave is a disturbance that travels through a medium, transferring energy without transferring matter. Or, this last sentence, you can change it to without causing any permanent disturbance to this medium itself. That's wave for you. We have to understand wave motion. Before we look at the types of wave, how they travel, we have to understand wave motion. All right? Wave motion and particle motion. We are going to look at both of them. All right? But before we do that, let's understand vibrating system as a source of wave. Vibrating system. Those of us who use vibrators should understand what I'm talking about. Remember, wave is a disturbance. Having said that, vibrating system as a source of wave. We have various vibrating systems as a source of wave. For example, tuning fork that vibrates. Okay, tuning fork vibrates, transferring energy from one place to another. Tuning fork, like this. Okay, it vibrates, transferring force, all right, through the coil it has from one place to another. We have other ones like loudspeakers, or the diaphragm of a speaker. Okay, diaphragm, okay, of a speaker, of a speaker. It's through vibration. Another one is a ripple tank. Ripple tank. A ripple tank produces small wave. All right. For example, let's say this is a bowl of water. All right. I'm demonstrating a ripple now for you. Then you pick a stone and you throw the stone inside this bowl of water. Immediately you throw the stone inside this bowl of water, you are going to see a wave of water in return, a rebound of water moving upwards. All right. Moving what? Upwards. And this is called ripple. Okay. Or you call it ripple. Ripple. You can also call it water wave. You can also call it small wave. So that's the demonstration of the ripple tank. Right. So let's progress. Wave. Let's also understand. We have understood wave as a vibrating system as a source of wave. Vibration as a source of wave. Now let's understand wave as a mode of energy transfer. Remember in our definition, we said that wave transfers energy from one place to another through a medium, right? So let's look at wave as, as a source of energy transfer, right? Looking at wave as a source of energy transfer, you move from a source through a medium without causing a permanent disturbance. This is the definition. Okay, so wave, let's say this is a medium. So wave moves through this medium. All right. It transfers energy as it moves, but it doesn't transfer matter. And as such, it doesn't cause no permanent disturbance to the medium. All right. No permanent disturbance to the medium itself because matter is not transferred. All right. Matter is not transferred, but the disturbance, wave motion, okay, particle vibration is transferred, which is the disturbance. All right. Wave motion is the motion at which the wave moves through the medium. All right. So let's quickly understand the differences, or let's just say the difference, because it's one major difference between wave motion and particle motion. The difference between wave motion and particle motion. All right. It's easy. For wave motion, or let's start with particle motion. For particle motion, there is just oscillation of particles. Okay. Oscillation. About oscillation of particles about an equilibrium. That's about a balance. All right. That's it. As simple as ABCD. Oscillation of particles about a balance, or about a particular, a particular position. All right. Then we look at wave motion. For wave motion is all about a disturbance. All right. A disturbance that travels through medium. All right. Disturbance traveling through medium. A disturbance that travels through a material medium, or some textbook can use another word. Instead of travel, they use propagated. All right. Propagated through a material medium. You can see different words. They all mean the same thing. You can still see another one we use spread. All right. Spread. So that's that for that. Understanding the difference between particle motion and wave motion. So in essence, particle motion is part of wave motion. All right. Particle is part of wave. For there to be a wave, there must be particle vibration. There must be particle motion for you to have wave. All right. So this one is just the oscillation that you see as the wave itself. Okay. As the wave. This particle motion is what you see as the wave itself. All right. But the wave is now the disturbance created by the particle. For example, by the particle motion. For example, this is a medium. Okay. Let's say this is an object, okay, a metallic object. Then I hammer this place. I use a hammer. All right. Let's say this is a hammer. I hammer this place, and you are holding here. Okay. The disturbance is transferred in form of wave, but this metallic object vibrates. That's particle motion. But that disturbance, as a result of that vibration, travels to this place where it is held with the hand, and you feel it that someone just hit something on this metallic object. So hope you understood the difference now between the two of them. All right. Now let's quickly observe. The relationship between frequency, wavelength, and velocity. But before we observe that relationship, let's just draw the diagram of a waveform here. All right. So let's use that one to define every other thing. All right. Waveform. Waveform is a diagram that shows how wave behave. All right. Or it shows the components of wave and how wave behave. That's waveform. So waveform diagram is usually a graph. This one is S axis. This one is Y axis. All right. So we have something like this. 1. Let's just leave it at 2. Okay. So we have to understand something. All right. This distance. Then which other one again? Let's say this is 0. Where is the direction of wave? Let's say this is the direction of the wave. All right. This is the direction of the wave. All right. So this is a waveform. Now, we have to understand something. All right. For frequency, there's something called frequency. All right. You see from here, remember frequency is oscillation per second. You see this one now. You see this one. One wavelength per second is known as frequency. So from here to here per second is known as frequency. From here to here per second. Remember, frequency is defined as oscillation per second. That's to and fro movement per second is frequency. It's given by 1 over time, right? 1 over second, right? So 1 oscillation per second. All right. And the SI unit is what? Hertz. All right. Hertz. That's the SI unit. Now, we have to understand another one called amplitude. Some textbook we say amplitude of vibration. All right. So amplitude is the maximum distance of displacement. You see, the maximum distance of displacement of a what? A crest or trough. The maximum distance of displacement. Maximum, max, distance of displacement of a what? Of, let's continue here, of a crest or trough. All right. So this is a crest. This is a trough. So what is a crest and a trough? A crest is the half of the circle, the half of the circle made, the half of the circle made by half part of a wavelength. That's the one located on top. The one called crest is located on top of the waveform. Then the lower half of the circle, this one, on the lower part is called trough. All right. So we are now free to define wavelength. All right. Wavelength. Wavelength is the what? Is the distance between two crests, between a crest and a trough. Okay, not two crests. Let's say between a crest and a trough. Between a crest and a trough. All right. So this distance between here and here is a wavelength. Between a crest and a trough is a wavelength, and it's usually indicated as lambda. This lambda. All right. That's wavelength for you. So in essence, we can have something like this equal to velocity over frequency. All right. So depending on what we are working with. So this is a waveform. Understanding waveform. That's what we are doing right now. Understanding waveform, because the earlier you understand this waveform, the better for you. The better you are going to become at what you do. All right. So it's very easy. I've simplified it. Waveform. So understanding the relationship between frequency, amplitude, and wavelength. You know, this is lambda, okay? This is lambda. So the relationship between frequency, amplitude, and wavelength is, you know, the amplitude is the maximum distance of displacement. Okay, let's just keep amplitude away from this. Let's just say the relationship between frequency, wavelength, and velocity. All right. So relationship between frequency, wavelength, and velocity. That's it. So how do we write this relationship now? It's just to connect them. Velocity is equal to lambda, frequency times lambda. Okay, frequency times lambda. This is the relationship. All right. So from this relationship, you can write out the formula of any of these. You can write out the formula of frequency, depending on what you are solving. All right. You can write out the formula of wavelengths and so on and so forth. So this is the relationship between frequency, wavelength, and velocity. All right. Remember that wavelength is usually measured in what? In meters. All right. Wavelength is measured in what? Meters. Okay. Wavelength is measured in meters. Then what are we looking at here? All right. Let's continue to phase difference. Phase difference in angle. The angle between 2 points in a wave. The angle between 2 points in a wave. All these angles. Look at it here. This one. All these are phase differences. All these are angles. All right. All these are angles. You see, all these are angles. They are known as phase difference. All right. Phase difference. Phase difference. All right. It's usually indicated as something like this. Phase difference. So that's that for that. Let's look at the formula of wave number, because sometimes, you know, they are commonly set in College of Nursing Sciences exam. That's why we have to master this wave. It is very, very significant to our job as a nurse. All right. Most of the equipment we use, they run under the principle of wave. Wave number is known as K. Wave number. Wave number is known as K. And this wave number is equal to, or K is equal to 2 pi over lambda. All right. Where pi is equal to 22 over 7. Lambda equal to wave length. All right. That's that for wave number. Then wave vector is a vector quantity showing direction of wave. The magnitude in a wave vector is a diagram showing the direction of wave. For example, this is a diagram. This is a wave vector. The direction of the wave. This is a wave vector. What's the direction of the propagation? Okay. So this is a wave vector. So the magnitude, remember what I told you is magnitude, strength or trajectory. All right. The magnitude is known as the wave vector. The magnitude is known as the wave number. All right. The magnitude, the direction. It's not the direction, the strength, the trajectory, the movement is known as the wave number. So this is the wave number. This is the wave direction. All right. Let's quickly look at progressive wave. Before we look at classification of wave, then we look at the properties of wave or the characteristic of wave. All right. Let's look at progressive wave first of all. Progressive wave. Progressive wave. Very important. Progressive wave now is a wave that changes as it moves. As the wave is propagated, it changes as it moves. As it goes, it changes. So it has an equation. All right, there's an equation. Y, this one is the most common equation. We have another equation that you use to solve. Y is equal to A, which is amplitude sine brackets 2 pi lambda, 2 pi over, let's just put it in a way that 2 pi over lambda plus or minus, okay, plus or minus S over Y. All right. So this is progressive wave. This same progressive wave, you can still write it as Y is equal to A, which is amplitude sine bracket open K minus S bracket close. All right. This is also the progressive wave equation. You can also write it as Y is equal to A sine bracket open Kx plus or minus Vt. All right. So all these are progressive wave equation, depending on what you are looking for. But there is a standard for the progressive wave equation. All right. There is a standard for the progressive wave equation. Using progressive wave equation to solve is very easy. Very, very easy. All you need to do, you just have to substitute. We are going to look at that. Before we write out the standard wave formula, the standard progressive wave formula, let us write out other formulas for progressive wave. All right. We are going somewhere. Just relax, because this progressive wave is something that one has to master. If you don't master it, you start encountering problems. So, other formulas of progressive wave, we have, I just don't want to forget any of them or to leave out any of them. So we have Y is equal to A sine bracket open. This Y can be X, okay? It can also be S. S can be used here. So we have 2 pi over lambda Vt minus S. So 2 pi over lambda minus Vt minus Vt over X. All right? Minus Vt over S. So where X, this X is equal to wave position. All right? V is equal to velocity. All right. Which other thing? T is equal to time. All right. 2 pi. We already know what pi is. This lambda is equal to wavelength. All right. A is equal to amplitude. Amplitude. All right. So the Y is the progressive wave itself. All right. So wave position, wave frequency. All right. So that's that for that. So the next formula that we are going to look at for is the next progressive wave formula. Since we are using velocity here, you can also rewrite this, what we have here. You can rewrite this as using minus. Okay, you now put this one in brackets. All right, so you're not going to have 2 pi over lambda minus, depending on what you are solving. Don't get confused. Minus brackets open. Vt minus x. It's just basic mathematics. Okay, depending on what you are solving. Okay, you can also use this one. Okay, then let me show you the standard progressive wave equation where we have phase difference. Okay. So y, oh, this marker. So y is equal to a sine, okay, let's use capital letter A, sine, bracket open, angular frequency t minus kx. All right, where a is amplitude, talked about that before. Sine is the angle. This thing like nyash is equal to angular frequency. All right, x is known as wave number. X is equal to wave number. All right, angular frequency is measured in radian. The unit is radian per second. Remember, it's frequency, radian per second. Because it's frequency, we are going to measure it with what? Radian per second. All right, then for wave number, it's measured in radian per meter. Don't forget that. All right, so this is the standard progressive wave equation. So if you are given a question to solve, let me look for one question here. Here we applied something like that. Frequency. Okay, so do not forget that angular frequency is equal to 2 pi over lambda. Okay, 2 pi, the frequency. This is the formula for angular frequency. So if they tell you to find angular frequency, that's the formula. Then frequency itself, f, we bring frequency here. We are now going to get equal to 2 pi over the angular frequency itself. Okay, 2 pi over angular frequency. That's the frequency itself. The ink of this thing is just too much. The ink is too much. Okay, I think we'll have to rewrite this. It's too much. So the frequency itself, we are bringing frequency here, is equal to angular frequency over 2 pi. As simple as that. All right, so let's bring it to the top. So before we do that, I want to wipe this place now. Let's look at a typical example of how we use the progressive wave equation to solve a question. All right, for example, we are given a question in the wave equation above, find so thing. All you have to do is to just find the coefficient of what you are told to find. If you are told to look for time, for example, look for the coefficient. For example, maybe you are given a progressive wave equation of y is equal to 0.2 sine brackets 200 pi t minus 10 pi x. All right, they now ask you to find, they can ask you to find anything. They can say look for the amplitude, look for this one, angular frequency, look for time, look for, just know if you are asked to look for wave number is the what? Is the coefficient of k. If you are asked to look for time is the coefficient of this one, of angular frequency. If you have to look for angular frequency is the coefficient of time. For example, using this, you are going to use this standard wave and progressive wave equation to find everything. So you are going to rewrite everything like this. You are going to say y is equal to, no need to rewrite because we already have it there. Okay, so what this means is that y is y, a is this thing. Okay, the coefficient of sine is a. So here, this one, angular frequency is 200, is the coefficient of what we have here. All right, then t, so 2 pi is likely the angular frequency, right? 2 pi. So t, they can't ask you to find t because t wasn't indicated here. But should in case they ask you to find t, you are going to rewrite this. You are going to rewrite this formula, any of this formula. Okay, you derive a formula from this. So you are now going to have something like t is equal to v times x. Okay, v times s, something like that. That's what you are going to have. Okay, or you are going to have t is equal to 2 pi v over x. All right, so depending on the circumstances, that's why you have to look at your parameters, the parameters given to you to solve with. All right, so calculation is what they bring most of the time is this equation. They will ask you to look for coefficients. Okay, so you have to know the standard progressive wave equation. So if they ask you what is k, k is what? Coefficient of s, which is what? 10 pi. Okay, 10 pi. 10 times 22 over 7. Okay, that's it. As easy as that. There's nothing difficult about progressive wave equation. Nothing difficult at all. Nothing difficult. Nothing difficult. So do not forget that period, that's T, capital letter T, known as period, is equal to 1 over frequency. All right. So that's the formula for period. K is wave number. All right. What are we looking at? I think we should now progress to the types of wave or the classification of wave. All right. Let's understand the classification of wave next. Classification of wave. Wave can be classified as either mechanical or electromagnetic. It can be classified also as longitudinal or transverse. All right. Let's understand that right away. So, classes of wave. Like I said, it can either be mechanical or electromagnetic. Mechanical or electromagnetic. You know what it means to if something is electromagnetic. Okay. Then 2, it can either be what? Transverse / longitudinal. So if it's whether it's transverse or longitudinal, it all depends on what? It all depends on one thing, which is the what? The direction of propagation, the direction of transfer of that disturbance. That's what determines if it's a transverse or a longitudinal wave. All right. So mechanical wave usually requires material medium. So for mechanical wave, this one requires material medium. Any wave that requires material medium, such as water wave, sound. All these are mechanical wave. All right. Water and sound wave, they are all mechanical wave. Then another one is electromagnetic wave. This one, no material medium. Does not require, let your people know, no material medium. Should we use material medium? Let's use medium now. Doesn't require medium. No medium. So mechanical wave, medium. Electromagnetic wave, no medium. It's an opposite. Example is light wave, light / radio. So you know the electromagnetic waves now. The Roy wave. Is it Roy wave or Rivos G? Rivos G. Rivos G. Rivos G. All right. So this is it. Rivos G, the electromagnetic wave. Radio wave, infrared. Sometimes you can have the one they call microwave together with it, but that one is no longer standard again. So we have visible light, we have ultraviolet ray, we have X, which is S ray, and G, gamma ray. All right. So that's that for these two. Then let's look at longitudinal and transverse wave. All right. One is parallel and the other one is perpendicular. This one, longitudinal, like I said before, is according to the, I want to wipe this off, according to the propagation, okay? The direction of propagation. That is what you have to note about longitudinal and transverse wave, all right? So for longitudinal wave, we have parallel propagation, all right? The particles vibrate parallel to the direction of propagation. All right, particles vibrates parallel. Don't forget this parallel. Parallel to propagation. Or to the what? To the direction of propagation. To the direction of propagation. So it vibrates parallel. Okay, so like this. Okay. Then for transverse wave, is very simple now. It's opposite of this one. Opposite of parallel propagation or parallel line is what? Perpendicular. Okay, perpendicular. Perpendicular. So the particles vibrate perpendicular to the direction of propagation. So we are not going to have interception, right? Interception. Some particles are going like this, while some are going like this. So example of transverse wave is like sound. Example of longitudinal wave is like sound wave. All right. Parallel. All right. To the direction of propagation, the direction of spread. All right. Why this one we have water wave and light wave here. Under transverse wave, you can have water wave, water and light wave. Light waves. All right. So that's that for the classes of wave. We also have stationary wave and progressive wave. We already talked about progressive wave, but let's look at two of them together. Okay. Always treat them according to the way they appear. Opposite of this one. We started with mechanical wave and electromagnetic wave. Then we entered longitudinal and progressive. Now we are going to stationary and progressive. Okay. One is stationary wave. Stationary wave. The other one is progressive wave. Progressive wave is continuous propagation. All right. Continuously. Transferring energy continuously. Energy transfer continuously. Through what? Through medium. All right. That's for progressive wave. Therefore, stationary wave, we have produced by superimposition of two waves of same frequency traveling in opposite direction. So here is where we have the node and antinode. All right. So just know that there is an opposite direction of travel in this stationary wave of travel or propagation. All right. And it has what? Same frequency. Two waves of the same frequency. Two waves of the same frequency. Two waves of the same frequency. Frequencies. So don't forget that. All right. So that's that for progressive wave. An example for stationary wave. An example of progressive wave is like the wave you see in a stress string ropes, ripple tank, and so on and so forth. All right. Let's quickly look at the characteristics or properties of wave. The characteristics and properties of wave. I think this is going to be the last subtopic on wave. The characteristics or the properties of wave. So for this, I will be on the right. Characteristics and properties of wave. Okay. It can be called properties or characteristics of wave. All right. The first we are looking at here is reflection. We have reflection. We have refraction. We have interference. We have diffraction. And there's one other stuff called superimposition, plane polarization. Okay. Superimposition, plane polarization. All those are just other aspects that we have to look into, but they are not majorly the properties or the characteristics of wave. All right. But let's look at these four major characteristics of wave. We also have a polarization. All right. Polarization. Okay. The 5 characteristics of wave. All right. So reflection is a rebound of wave. So when a wave rebound, wave fall on a plane surface and rebound. That's what reflection. For example, this is a plane mirror. A wave from my image falls on the plane mirror. It hits the mirror and it rebounds. Okay, this is an incident ray. This is what? A reflected ray. Okay, can you see the direction? All right, so that's for reflection. Then the next is refraction. It is not a must that the surface will be a mirror for reflection. Any surface that is capable of rebounding wave, all right, such as light surfaces like this board, the white wall, and so on and so forth, will reflect wave. All right. The next is refraction. This one is the what? The change in direction of wave when it passes into a new medium. Let's say a medium of new speed. Okay. The change in what? Direction. In direction of wave when it passes through a medium of different speed. Different speed medium. Different speed medium. A medium of different speed. So for example, I point light towards let's say this is air. This is air. Then this is water. All right. So when I point light from air to water, this is a medium. Air is a medium. Water is another medium. So when I point light here, the light falls on it passes the air medium and enters a new medium. Remember, these two mediums have different speeds. Okay. They have different speed. Okay. So the speed of light in air is different from the speed of light in water. All right. So the speed of light in air is just like the speed of light in vacuum. Okay. It's different for the speed of light in water. All right. So this is immediately the wave enters here, is going to refract. All right. How does it refract? It's going to change. The direction of the wave is going to change. All right. It's going to change. So it's going to bend as it enters the water, as it crosses this medium, because it has a different speed. It bends. All right. This is a new direction of wave. All right. You know that water is a denser medium than air. So water will likely bend a wave. Okay. It's likely going to bend a parallel wave. Okay. Focused on it. So that's that for that. The next is interference. This occurs when wave meets or overlap. Okay. When two waves meet or overlap. All right. When two waves overlap. All right. That's interference. For example, this one is a waveform. Okay. This one is one wave. All right. In the same waveform again, you still see another. This one is still another waveform again. Two waves. Okay. This one is interference. Two waves meet and overlap. Because they are moving towards the same direction at the same velocity. This is called a constructive interference. Constructive. Okay. We have the one called destructive interference, whereby both waves are moving, though they might be moving in the same direction, but they are not moving in the same velocity. All right. They are moving in the same direction, but they are not moving in the same velocity. The amplitude is cancelled. All right. One is up, the other is down. Let's look at the example. So here we have something like this. Two waves, right? They are moving like this. Okay. But for destructive, you are not going to have something like this. One will be up, the other one will be down. Okay. One will be up again, the other one will be down. So this one is destructive. Okay. Destructive interference. All right. The next one we are looking at is diffraction. When wave, especially light wave, bends when it passes through a narrow opening. Okay, the bending of wave. When it passes through a narrow opening. All right. So let's say this place is dark. Okay. Or yes, this place is dark, but there's just a small hole here on the wall of this board. All right. And we point a light, okay, on that small hole from the other side. Immediately that light passes this small hole, it's going to spread. It's going to spread out in this room. Okay. That's called diffraction. Okay. Diffraction. All right. Also, diffraction is also when you point light into a curved or bent surface. Okay. Maybe this is the light. Okay. When you point light here into this place, when the light gets here, it's going to bend. That's what diffraction too. It's going to bend. Okay. Because it's passing through a narrow surface. All right. It all depends on the narrow surface that the light is passing through. All right. So the final one here is polarization. Polarization is restricting the vibration restricting vibration of a wave, usually light wave, to a plane. That's why most of the time it's called plane polarization. So what is the application of polarization? It is used to do what? To reduce the intensity of sun, like in sunscreens for vehicles, aeroplane, spectacles, glasses, all right? Because it restricts the vibration of wave. It restricts the extent of vibration of wave, thereby affecting transfer of the wave, propagation of wave. It's usually done using a plane surface. It could be a mirror, plane polarized mirror, or plane polarized glass to form a plane polarized wave or plane polarized light. All right. So we have superimposition. Okay. Superimposition explains interference. Okay, where two wave meets and overlap. All right. Where two wave meets and what overlap. All right. Let's now enter sound wave. Understand some few stuffs about sound wave, like beats. Beats. What is beat? Beat is a periodic vibration in loudness when two waves of slightly different frequencies interfere. Remember, the two waves have what? Slightly different frequencies. That's why it's called beat. Okay, it's a periodic vibration of loudness. Loudness go high one side, it go low the other side. Involving two waves of almost the same frequency. Okay, close frequency, waves of close frequency. That's where you see beat. So what I'm just explaining right now is the difference between beat and noise. All right, beat and noise. In noise, the frequencies are not close, are not anywhere close. Okay, the frequency of the vibration of the loudness are not anywhere close. Okay, that's for noise. All right, so beat frequency is equal to difference between frequency. Beat frequency is equal to difference between frequencies. All right, Doppler effect is the apparent change in frequency of a wave due to relative motion between sources and observer. Okay, the apparent change, that change that you can see, Doppler effect, is that change that you can see, the apparent change in frequency of a wave due to relative motion of the source and observer. So when, remember what I told you about relative motion, all right, of the source and the observer. What is the source? The source of wave is where the wave is coming from. The observer of the wave is, this one is the source. The observer of the wave is the material that is observing the wave. For example, you slap me. The source of the wave is your hand. The observer is my cheek. That's the observer of the wave. What experiences the wave? That's the observer. That's a Doppler effect. So the source approaching gives a high frequency. The source receding, that's the source receiving it, gets a low frequency. So when it's coming from the source, the frequency is usually high, right? As the slap they come, is usually high. So when the slap lands on my face, which is the observer, frequency is usually what? Lower. Okay, as simple as that. The application of Doppler effect is in radar, astronomy, and speed detection. Radar, astronomy, and speed detection. All right, so that's that for wave. If you have any question on wave, do not forget to drop it in the, remember where we, do not forget to drop your questions in the group. Remember where we have node and antinode is in stationary wave. All right, stationary wave is where we have node and antinode. I just remembered something that we haven't treated sound wave yet. Sound wave is very important because it is very applicable to what we use in the hospital. Okay, what nurses are involved in is very applicable to nurses. Very, very significant in the profession. So let's look at sound wave. I'm likely going to see questions from this sound wave. All right, sound waves. All right, sound wave. What is sound wave now? The wave produced by sound, right? So how is sound wave propagated? It is propagated when the material that is needed for its propagation is present. Okay, and what are the necessary material medium for sound wave propagation? Since sound wave is a mechanical wave, the one that requires mechanical wave, the one that requires a material medium, it requires a material medium to be propagated, right? So it requires particles to vibrate and transfer energy. Okay, it requires particles as a what? As a medium. Medium is what? Particles. Okay, to vibrate. All right. And also, sound can't travel what? In a vacuum. It's not like light that travels in a vacuum at 3 times 10 raised to power 8. No, sound can't travel in a vacuum. All right. The speed of sound in various medium like air, it travels in air. Remember, vacuum is an enclosed space, airtight space, but air is air, the atmosphere. All right. So the speed of sound in various medium determines how fast sound travels. The heavier the medium, the faster sound travels in that medium. So in a solid medium, so you should expect that the speed of sound in a solid medium should be higher, because solid is what? Denser. In a liquid should be a bit higher than air, right? So air is the lowest. Air is the lowest. So at most solid, like in iron, sound will travel at 5,000 meter per second. 5,000 meter per second. Okay, that's roughly 5 times 10 raised to power 1, 2, 3 raised to power 3. All right. In solid, that's in iron. Then in liquid, sound will travel as fast as 1,500 meter per second. All right, that's about 1.5 times 10 raised to power of 2. All right, which one is the next one? Air. This one is like 500 or so, 340 or so, which is air is the slowest, 340 meter per second, roughly 3.4 times 10 raised to power of what? 3.4 times 10 raised to power of times 10. It's just 3.4 times 10 raised to power of. If you put raised to power of 1 here, it's going to turn to something else. So let's just put 340. All right, 340 meter per second. All right, so that's that for the speed of sound. Like I said, the density, the density of the medium determines how fast sound travels. The heavier the density, or the more dense the medium, the faster sound travels in it. All right, so the effect of temperature and pressure on sound. Effect of temperature and pressure on sound. Effect of temperature and pressure on sound. Effect of temp/pressure on sound. Okay, so the speed of sound in air increases with temperature. So in air it increases with temperature. All right, then in fluid or pressure has, this is what in air, that's where the temperature usually affects. Okay, air. But the effect of temperature and pressure on sound is negligible. All right, meaning that there's not enough evidence to say it's high or low, or that temperature and pressure has an effect. Okay, so just know that temperature affects the propagation of sound in air. So in air, it usually increases, the propagation of sound or the spread of sound in air usually increases as temperature increases. So in a hotter place, sound will travel faster. So understanding the reflection of sound wave, we already spoke about reflection, right? So understanding the reflection of sound wave, we have concept like echo. All right, and what is echo? Echo is the reflection of sound wave in a plane surface. So when sound wave fall, let's say this is a plane surface, sound wave fall on this plane surface, it falls and it rebound. Is that not a reflection of sound wave? All right, that's echo. So when you come out and shout at an enclosed place, okay, you are going to hear the echo of your voice, because your voice fall on the plane surfaces, on the wall, and it bounces back and you hear the sound of your voice. That is what echo. And the speed is usually occurs in 0.1 second. All right, 0.1 second. After you shout, you hear your voice, you hear the rebound of your voice, usually 0.1 second. Okay, and the distance of echo is usually greater. The distance is usually greater. Let's put distance is usually greater or equal to 17 meters. All right, don't forget this. So they always set this. Okay. Then we have another concept under this reflection of sound wave called reverberation. It's not revibration, it's reverberation. This one is collection of echoes. Okay, collection of echoes. Collection of echoes for a prolonged period of time. So echo plus echo plus echo for a what? For a long period. That's reverb for you. And what is the application of echo and reverb? Echo is applied in ultrasound. I don't know if you have done ultrasound before in the past. That's where you use echo. In ultrasound, it's a scan used to view the internal structures of the body, especially soft tissues and organs. All right. It's also used in distance measurements to measure distance. All right. That's that for that. Then for reverberation, it's used in musical instruments. To produce quality sound. Also used in sound engineering. All those music producers. They use reverb to increase the quality and richness of sound. What are the advantages of echo / reverberation? It is used in medical diagnosis, like I said before, in medical tests, imaging tests, and also in musical instruments. It's also used in to determine length and navigation. What are the disadvantages of echo and reverberation? Noise. Noise, it affects communication, distorted speech. Speech no go clear again. All right. It's also a source of noise pollution. Noise pollution. And it gives unclear sound. We already talked about that. Distorted sound that is not clear. Let's now look at the characteristics of sound wave. All right. There are important aspects we have to understand in this sound wave. Characteristics of sound wave. I think this is going to be the last one for this part. So under the characteristic of sound wave, all right, under the characteristics of sound wave, we have to understand noise and musical notes. All right, for noise is irregular. Is irregular, and the difference in frequency is usually high difference in frequency of various notes. All right, unpleasant vibration. The difference in the frequency of the particles is usually very high. So then for music note or musical notes or beats, is regular. Well constructed, the frequencies are usually almost the same. Almost the same. The frequencies of the frequencies of the particle, the vibrating particle, is usually almost the same. So it forms something called harmony. Harmony is formed. All right, during music notes creation. Now let's look at the characteristics of sound proper. We have pitch, we have intensity, we have loudness, we have quality. Quality is also called timbre. Okay, so the first one, number one, is pitch. The pitch depends on high frequency. So high frequency equal to high pitch. High frequency equal to high pitch. So remember that pitch always depends on what frequency. Then they always set questions from here. Then the other one is intensity. So this one is like the energy per unit area per unit time. So the energy per area per time. All right, energy per unit area per unit time. It usually depends on what? Amplitude. All right, so pitch depends on frequency, intensity depends on amplitude. All right, depends on amplitude. Then number three is loudness. What is loudness? How you perceive sound. How you perceive sound. You can either perceive it as loud or low. Okay, how sound is perceived. How sound is perceived. Then number four, we have the one they call timbre. Sound quality or timbre. This one, we can call this one overtone. All right, overtone. overtone. Then we have timbre, quality or timbre, quality slash timbre. Okay. This one is what distinguishes sound of the same pitch and loudness from different source. So this one usually depends on overtone too. Okay, this one depends on overtone. Quality and timbre depends on overtone. It distinguishes sounds of the same pitch and loudness from different source. Okay, so if the sound is coming from source A, another sound is coming from source B, it distinguishes the sound. You can be able to tell that timbre is going to allow you to tell that this sound, though this sound is the same, is coming from this medium. This one is coming from this medium. I can hit this thing. This one is the same sound, right? But if I hit it here, it's the same sound, but it's coming from another direction or another source. Coming from another source. So that's that for that. This usually depends on overtone. So pitch depends on frequency, intensity depends on amplitude, then quality or timbre depends on overtone. All right. What are the applications of the quality of sound to musical instruments? Pitch control, helping to control pitch. And how do we control the pitch? Remember, it depends on frequency. So if we can control the frequency of the string or the instrument, we can control the pitch. So if we tighten the string, it gives a high pitch. We free the string, or we loosen the string, it gives a low pitch sound. All right. So we continue. The second application is loudness, which is controlled by amplitude. Okay, loudness is controlled by amplitude. Remember, amplitude is the maximum distance of displacement. Okay, maximum distance of displacement. That's amplitude for you. So loudness is also controlled. That's why this intensity, you want to resemble loudness. So it's also controlled by amplitude. Remember the waveform diagram. This is amplitude, maximum distance of displacement. So we are going to get the loudest here. Okay, so it depends on amplitude. All right. So the quality of sound, which is this one, is determined by overtone. So do not forget, overtone is also known as harmonics. All right. Overtone is also known as harmonics. Now the same thing there be. All right. So harmonics and overtone. All right. Integral multiple of fundamental frequency. Integral multiple of fundamental frequency. That is what harmonics. Then overtone is higher frequency produced along fundamental frequency. Though they are almost the same, but there's a slight difference. You understand, between overtone and frequency. But then in school, we were taught that overtone is harmonics. Okay, that was why I just remembered and I indicated it here. But there is usually a slight difference between overtone and harmonics. Integral multiple of fundamental frequency. So you times 2 fundamental frequencies to get what? Overtone. To get harmonics. We are going to look at the open and the closed pipe right now. All right. Therefore, overtone is higher frequencies produced with fundamental. Okay, higher frequency. So frequency times fundamental. Fundamental frequency. Okay, it's usually represented with something, whether X or so. Okay, then that's for overtone. Overtone. All right. So vibrating string and air column produces harmonics. Remember, harmonic is produced from musical notes. Okay, it is structured, it's periodic. Okay, closely, almost the same frequencies. All right. So do not forget that. Resonance. Resonance is when frequency of external force. Remember when I taught you, frequency of external force equals natural frequency, or driving frequency equals natural frequency. That is resonance. Okay, and during that amplitude increases greatly. So when it happens, amplitude increases greatly. So what is an example of this resonance? Tuning fork with resonance bus. Tuning fork plus resonance bus. All right. This one is an example. Another one is an organ pipe. Another one is breaking of glass by loud sound. Breaking of glass by what? Loud sound. So when the external frequency equals the frequency of the system itself, the glass shatters. That's coming from the sound. So we are looking at the open and closed pipe harmonics. That is inside the frequency note in air column. All right, frequency note in air column. The open and closed pipe harmonics. That's what we are looking at now. Remember, we talked about something called the node and the antinode when we were discussing stationary wave. We talked about node and antinode when we were discussing stationary wave. All right. So node is opening. Node is opening or is open. Antinode is closing or close. So note this. So when discussing about the closed pipe harmonics, we have to understand the closed pipe harmonic, the fundamental frequency of the closed pipe harmonic. Okay, usually the odd. Why the open pipe is closed pipe is odd. Okay, odd harmonics. Why the open pipe is all the harmonics itself. Okay, for example, let's draw the closed pipe harmonic first of all. Closed pipe. All right, this is a closed pipe. This is a closed pipe. All right. So here is what? The antinode. Here is the what? The node. You can see that the node is open, right? But the antinode is now found inside. So the pipe is closed. Okay, it's closed. All right. This one is antinode, closed blockage, node open. All right. So remember, this is odd numbers or odd harmonics. Do not forget that. The formula is giving us the fundamental frequency is equal to V, which is velocity over 4L. All right. Here this one stands for the length. Okay. V is the speed of sound or the velocity of sound. Where F equal to fundamental frequency, F equal to fundamental frequency. Fundamental frequency, V equal to speed of sound. Then L is equal to length. So what are the harmonics we have? So let's say we have 1 to 9 harmonics, for example. We have 1, that's 1L, or 1F. Let's say we have 1F, we have 2F, 3F, 4F, 5F, 6F, 7F, 8F. These are the harmonics, so 9F. So if we are looking at closed pipe harmonics, remember it's the odd harmonics. If you want to pick your frequency that you are going to use to calculate, or you want to pick your harmonics, you are going to pick all the odd numbers. Okay, we are going to pick 1, 3, 5, 7, 9. So if they ask you how many harmonics do we have, how many in a closed pipe, how many harmonics do we have from 1 to 9, for example? Okay, so we only have 1, 2, 3, 4, 5. So we have 5 harmonics. So F, which is frequency, equal to what? 5. All right. So we have 5 harmonics because it's only the odd. All right. It's only the odd. So when we look at open pipe now, open pipe is all the harmonics itself. All the harmonics. 1, 2, 3, 4, 5. All the harmonics. All right. Let's look at open pipe. So open pipe is like this. Is it? Yes, open pipe. So here is the node. No, here's the antinode. Here's the node, open. All right. So this is an open pipe. All right. The frequency, fundamental frequency, is usually equal to calculate the harmonics 2L over V. Right? Or V over 2L. Let's say V over 2L. All right. Where V equal to speed of sound, F equal to fundamental frequency, L equal to what? The length. All right. So if you want to calculate the harmonics, it's everything, all harmonics, all harmonics, everything will be included, all. So if they ask you how many, you say it's 9, depending on what you are giving. All right. So that's that for sound wave. I will see you in the next episode where we are going to continue with the next topic right away.